Yeah? Are we good? Ready for spring break? Yeah, I'm really ready. I take like my last midterm of the semester tonight. And it's gonna be so nice after. Sorry for you guys, but I'm only taking 3 classes this semester, and one of the classes I'm taking doesn't have exams. It's like a project-based class. Yeah. So, moral of the story is don't scam yourself. Take your time here and like take however many classes you want to take or don't want to take. Especially if you're doing like the CS degree or just the CS and the EECS degree, you can do it pretty quickly. So if you take your time and you don't rush, you'll end up like me where you don't have any more midterms after today. Okay. So fill out the attendance form. Couple of announcements. You want a worksheet? Couple of announcements. Homework day is due Thursday. This homework explores the type of graph traversal without really telling you yet what exactly that graph traversal is, but it's interesting. So you're going to implement this A-star search, which is a very interesting search algorithm where given like a graph, you try to find like the shortest path to something. In this case, you try to find the shortest path to like your target word. And then the mid-semester survey is linked on Piazza. You get, is it extra credit? I think you get extra credit for doing the survey. So Piazza thread 3191. And I'll read mine and debrief with everyone next week, so after spring break. I already read through one, and then I'll tell you guys next week. But yeah, do the survey, get extra credit. Wow, it's dark in here. Are you trying to lift it up, or do you? Oh, okay.
No, it's like really sunny out here.
Oh, okay, cool. Alright, we get to have class in the dark. Let's do basic operations. Let's just spend like the first 2 minutes. Actually, let's spend the first 5 minutes doing these two. So this is deleting from a binary search tree, and this is deleting from a min heap. So, okay, how do we feel about this problem? Who remembers like how to delete from a heap? Because I didn't when I looked at this worksheet. So it's okay, we'll go over it. But before we go over it, I have something fun to show you that I learned in my practical network class today. So, does anyone know what an RFC is? An RFC is something established by IEEE. This is normally how you basically outline a networking protocol. So, for example, if you've heard of like TCP, IP, HTTP, like these are all kind of familiar. They're all networking protocols that have like a spec in an RFC. So there's 3 RFCs that talk about certain network protocols for over avian carriers, so over carrier pigeons. It was an April Fool's thing, but they're like very serious about it, and they're like, we could do weighted fair queuing by actually weighing the pigeons. But yeah, it's all like super like it's really extra. But the cool thing is that I thought it was like funny because you know, it's like it's so dumb, but there's this one picture that's like a packet loss example. It's like it's a dead pigeon. Okay, all right, back to the worksheet. So take 168 if you want to know more about networking protocols. Why is this relevant? Because you guys will do graphs eventually, and you'll see that the internet is actually just a huge graph problem that people are still solving. Okay. So let's delete from a BST. So what is our protocol for deleting from a BST? See what I did there? Okay. So what nodes can we like, especially when we're deleting like the root of the BST, what nodes can we promote to be that new root? So, right, so this is the greatest here, or we can promote the smallest. Here. Does that make sense? Because if we put the greatest element here, then everything to the left will still be less than or equal to the greatest element. And then if we put the smallest element here, everything to the right will be greater than to the, yeah. That makes sense? So that means what nodes can we choose? Right, so here we choose the rightmost, which is 19. And then here we choose the leftmost, which is, 23. So I'll draw out 2 trees, so like both answers are correct. So first let's draw out the one with 19 in it. So 19, 15 goes here, 17, 16, and then what do we do with the 18? Yeah, we just stick it here. We just like move it up where it used to go. And then the other half stays exactly the same. Now what if we put 23 up here? So we know the left half stays the same. And then the 29 is going to go here, 25, 28. Where does the 24 go? Yeah, it goes where 23 was. And then 35 and 33. Huh? Oh, 24. Yes, good catch. So does anyone have questions about deleting from a VST? So when you delete from a VST, it's called like hybrid deletion, where you find either the greatest node on the left side or the smallest node on the right side, and then you just make that your root. Yeah.
In general, should we just know how these work, or do we need to know how to implement?
I think in general you should just know high level how it works. Implementing is like, you guys are gonna implement a min heap in lab, so you guys will implement it in lab. So it's like you can be tested on it, but I think the implementation comes a lot easier from understanding like conceptually what you're doing. Any questions? Okay.
So how would these two connect?
Huh? These? Oh, these are just two separate trees. Like they're both correct
Just be
answers.
set separately?
Right, because we could have picked either node to be our new root.
Okay.
Okay, so now for min heap deletion. What's our policy? So remember, what are facts about a min heap that we have to kind of like put in place?
Each child is bigger because it's
Right, so the child is bigger than the parent. But then, what's one other property?
the root's always small.
Oh, that follows from the child being greater than the parent. So, yes, completeness. So what does completeness mean? It means that like you either have like the structure left to right where like every level is complete. So like here we have one and there's two children and these all have two children. So it's like before you increase your height, you have to make sure that like your level has like maximized the number of children. Like so like either have like 0, 1, or 2 children, and the only time where you can have one children is if you're like still building up the last row. Does that make sense? So then when we delete from a heap, you guys learned during lecture that to maintain completeness, you just sort of like remove the last element, right? Like to maintain completeness, I can maintain completeness of this tree by deleting this and then like sticking the 9 here instead of 0. So the reason we do that is because completeness is really hard to do without like just like taking away a node that's like that won't make your tree complete. It's like taking away a leaf, basically. Questions? So when we delete, Hug had a good slide where it's like you assassinate the president and then you promote like the most recently added thing, right? Or you promote like the lowest hanging fruit. And then you slim it down based on like what is the next best successor. So you remove the root and then you replace with like the lowest and the rightmost leaf. So in this case, our lowest and rightmost leaf, I'll draw it in red, is this 9 over here. Yeah? So then, now here's what our heap is going to look like. It's going to look like 9, 1, 4, 8, 2, 6, 8. Now this heap is complete, right? But it's not a min heap. So what we did was we pretty much satisfied completeness, but now we have to enforce the fact that the child is greater than the parent. Does that make sense? So then to enforce that, you pretty much just check out like the children and then you pick the next best thing. Right? You pick out like the best child. And the best child is the smallest child because the smallest child is supposed to be the minimum that's like swim to the top. So they like exchange places. So over here, my 9 should switch places with what? The 1 or the 4? Right, the 1. So let's switch places. So this is the process of swimming down that 9. So then now I have a 9 here, and then I have an 8 and a 2. So what should this 9 switch places with? The 2. So then this becomes a 2, this becomes a 9. And then that's like your new heap. Why do we do this? Because completeness is really simple when you just remove the node from like the bottom, and you still maintain completeness of like your n minus 1 nodes. And then you just only take like log n steps to delete, right? Because you only swim down at most to the bottom of the tree. And because it's a complete tree, the height is log n. Are we good? Okay. So then now take like 2 minutes to do this weighted quick union, and then we'll go over it. So let's come back at like 5:29. Do you want to go over? Yeah? Nah? Okay. So here we have, they just want us to do a weighted quick union. And the difference between a weighted quick union and a regular old quick union was that we wanted to keep our trees bushy, right? We wanted to minimize the height. So when you have a weighted quick union, you set the parent to be like, the set that you're going to union into is the bigger set. Does that make sense? So like if you have something that looks like this, and you got like a little dingly like set here that wants to union into here, you do this. Because this has less elements than this. Yeah? Okay. So the convention we'll follow is that we'll make like this like the parent node. So like if we're gonna connect 1 and 4, we'll just draw the line like that. And then we'll like promote this, we'll like make this like the root. That's just convention. It doesn't really, you could do it the other way around, and your set would look different, but like just like a different order, if you know what I mean. Okay, so when I connect 2 and 3, oh, that's big, okay. When I connect 2 and 3, same thing, right? And let's just highlight like what we think the roots are gonna be, so the parents. And then if I connect 1 and 3, 1's parent is 4, right? And then 3 is its own parent. Now because these are the same size, we're just gonna break ties arbitrarily. And I'll just say, hey, let's make 3 the parent. I'll just break ties by like the lowest number will be the new parent. Are we good with that? So then now that means 4 is no longer a parent, and 3 is like the parent of the set. It's like the big boss node. So then now if I connect 5 and 1, what you do is you're connecting 5 to 1's parent. Yeah. So then that means you have to search, you have to ask 1, hey, what's your parent? And then 1's gonna be like, my parent is 3. Or it's gonna be like, my parent is 4. And then you ask 4, what's your parent? It's gonna be like, my parent is 3. And you'd be like, 3, what's your parent? It's like, I'm the boss node. So then we draw 5 over here. And this highlight is just the root of our set. Are we happy with this? Yeah.
So, weighted quick union just means you do the rank thing, right? Well, if you're comparing sizes, that's like rank.
Size is like the actual size of the set.
Okay.
So not necessarily rank. Rank is like height, right? So.
Yeah, but I thought. Okay, but anyway, so then like, does weighted quick union do the path compression thing?
No.
Okay.
Yeah. So weighted quick union and path compression are different. Path compression, look at the slides after weighted quick union. So weighted quick union gives you this like log n runtime, and path compression gives you this log star n, or it's more tightly bound by like the inverse Ackermann function, but you don't have to know about that. You just have to know the bound of log star. Yeah.
What did you say the difference was between weighted quick union and regular?
Okay, so weighted quick union basically ensures that our set is like bushy, right? Because if you like quick union things in like this order, you could get like a very spindly tree. But weighted quick union, because you attach like the smaller set to the bigger set, you kind of enforce this rule of bushiness. Okay. Yeah.
It doesn't matter which one you select as the root, right? So could you select one as a root instead of 4?
In this case, it depends. So the only time where it wouldn't matter is when you had like two roots that were competing with each other. So like root selection there's a pattern to it, except when like there's like convention, and the convention could be like, oh, let's make the higher number the root if you're like just unioning two sets of size 1. Yeah. Okay. Any more questions? All right. Red-black trees. So, they were going over briefly in lecture, and they're saying like indicate red nodes with an asterisk. So the red node is going to be the node that's like at the bottom of a red edge. So we're going to do like convention as this. So if you have like a sticky edge here, then the node they want you to draw is like this. Does that make sense? And remember the sticky edge just like represents like a 3 node that's like glued together. So there's like 2 numbers glued together. And it's left leaning, which means that the sticky edges should be like leaning to the left. Yeah. So if I do like the first couple nodes for you, if I do 10 and 40, the sticky edge should be here. We're kind of like doing this conversion of a 2-3 tree to like a binary tree that represents like conceptually what our 2-3 tree is supposed to represent. So first, I'm gonna make all of my like edges red, and then I'll just put asterisks at the end, like after we construct our tree. Does that sound good? So again, because it's a binary tree, we know that the left element has to be less than or equal to, and the right element has to be greater than, right? So let's just like start constructing our tree from there. So we have like this 1040 node, so we're like done with that already. And then that 1040 node has something coming out of the left side, which is like a 5-8 node, right? Now, because this node is grouped together, what number should be here? Right, it should be 8, because we have a left-leaning tree. And if we want to stick our 5, like, if we want to glue our 5 to our 8, then we have to make sure that the 8 is glued to the 10. Or not glued to the 10, but connected to the 10. So now we have an 8 here, and then where does the 5 go? Yeah, to the left of the 8. So now it looks like this so far. We're getting somewhere. So then let's just like crawl down here, and then we'll put a 3 node. We'll put a 3 here. Oh, that's not supposed to be red. We'll put a 3 here, and is that a red edge or like a black edge? Yeah, it's black edge. So the edges we're gonna draw here are all gonna be black edges because all the nodes are like, they're like glued. They're whatchamacallit. They're not glued together, right? They're just independent nodes. So then what goes here? 6. And then what goes here? 9. Okay. So now we took care of like this side of the 10, right? And then now we have to take care of this side, right? Because the 10 now also connects to like a 15. So 15 goes here. Are we good with that? And then what goes here? 14. And then what goes here? 30. Why? Because left leaning. So what edge goes here? 20. Good? Okay? So then now we just have to do this side. So the 90 goes here. And then what goes here? 80 and 95. So the convention we just defined is that like the lower node of the red edge is going to have the asterisk. So I'm just going to mark the asterisk over here, and over here. Are we good? Any questions?
So doing this structure is better than doing 2-3 structure?
It's easier to implement. So the whole reason we do left-leaning red-black trees, and this is how Java's tree set is implemented, is because keeping track of like nodes that can grow is kind of cumbersome. If you saw the slide in that lecture about trees, of like just some sample code of like trying to attempt to do it, it's disgusting. So we have this instead, which is less disgusting, but still kind of hard to like wrap your head around because you're like, why am I coloring nodes red. That's weird, right? So, but you still preserve the same structure, basically. Yeah. Okay, so then now let's move on to this one, which is saying that show that the 2-4 tree corresponds to the red-black tree on the left. So 2-4 tree, same thing as a 2-3 tree, except now your nodes can have 4 elements in it instead of 3. Or it can have 4 children instead of 3. Yeah. So what I'm gonna do is go in with my highlighter and color all of the edges that are red here. Okay. So now this looks a little bit more like we're starting to glue things together, right? I hope so. Okay. So then, because my edge is glued here, what's at the top? Yeah, 10, 20. Okay. And then what's to the left of this 10? Yeah, 1, 5, 8. Why? Because we have these edges all glued together. So you have like this big juicy node that's 1, 5, 8. Good? Okay. So then now I go to the right side here. And then the 20 has something on the left, right? So I have like a little middle child here. And what goes here? Yeah, 12, 16. And then what goes here? Yeah. So for red-black trees, I wouldn't be scared of them. It just takes some practice to like convert between the two forms. But it's doable. It's like mechanical. Yeah. Do we feel like this is doable? On the midterm, by April 7th, let's hope this is doable. Yeah? Okay. So now take 5 minutes to think about, like, high-level conceptually, think about what to do for number 3, and then we'll walk through it together. This is the tree traversal problem, and I suggest, like, just think about how you should traverse this tree so that you swap the elements as you traverse them. So the big hint here is that you have to do this in linear time, which means you have to basically visit every node once or twice. Order constant times n and swap them. We need to figure out a way to go through this tree. It's left and right like halves, right? And then swap the numbers like as we're walking along the tree. So the way this question is like egging you to go towards is to use a stack. Because you get like a safe push method. So, you know, like if they give you a method that involves a stack, you probably want to use a stack. Now, you guys haven't learned about, what are you guys up to right now? Did you guys just start graphs? Okay, so do you guys know what BFS is? No, right. So you guys have just started graphs. And what you'll learn in a future lecture is that stacks are going to be used for this type of traversal that we call depth first search. You don't have to know like what that means right now, but what I'm going to tell you is we want to basically have like simultaneous like explorers going down both halves of the tree, right? Because we need to have basically 2 like explorers to like swap their numbers. So you're gonna have like I'm gonna have a red explorer here and a black explorer there. Yeah? And then like at the first run they swap. And then now the tricky case is that which nodes do we want to swap at this level? We want to swap this one and that one, right? Which means that our left explorer has to go left while our right explorer has to go to the right. You see where I'm getting at? Like they're kind of exploring in opposite directions because that's what the problem wants us to do. Like they want us to swap this, and they want us to swap this. These are on like opposite sides of the respective node. Yeah. So already you're going to have 2 explorers, which high level is going to be 2 stacks, right? There's going to be the left stack and like the right stack that we're going to pop nodes off of and swap their numbers. Does that sound reasonable? So you guys will have a better intuition of this once you learn like depth first search and breadth first search and all the fun graph searches you could do. But the intuition here is that we just need 2 things like traversing. So we just need like 2 pointers. And we need the 2 pointers to go in a very specific order, right? The left pointer has to go in the opposite direction of the right pointer. Make sense? So then let's just draw out what this traversal is going to look like. So our left explorer is going to go this way, right? and it's going to do some stuff. And then our right explorer is going to go this way, right? And then now you hit a dead end, right? So you have to go to like the next child, to the next node. Because you can't, there's nothing more to do after you're here, right? You have no more children to look at. So then that means our left explorer is going to go here, and then our right explorer is going to go here. Yeah? So that happened. And then again, notice how like the left explorer went to the right, and then the red one went to the left. So again, opposite directions. And then we now have to explore here, and then here. And then we just, like, every time we're done, like, every time we pop a node off, we just swap the two numbers. Yeah? So then this means when you start over here, you need to have two stacks. So we're going to have a stack called left and a stack called right. And then for the left stack, we're going to add root.left. And then for the right stack, we'll add root.right. So this is just to start our stacks off with something, right? Start off our explorers. Here are my two children. Go explore. So then we're going to have to, we're going to pop these like two nodes off, right? So we're going to like pop, we're going to pop the right, or we're going to pop the left, and then we're going to pop the right. And I should have written that in red. Undo. Okay, so then that means our two explorers are here and here. Yeah? And then now they have to start exploring in opposite directions. So our left one has to go to, it has to add, so we'll call this L, and then we'll call this R. Our left one has to go to the left first, right? So we want to add, like, onto its queue, the left node. But then what do we want to add to this one's queue, or stack? Because they're going in opposite directions. Yeah, we want to add the right. And the reason for this might not seem obvious yet, but just think about it as you want to explore in a certain order, and you want to explore the order such that you're going in opposite directions. Yeah. And then here we could have added like the left and the right. We could have added the left first, or we could have added the right first. We just have to make sure the other one does exactly the opposite. You know what I'm saying? So then now we add L.right. Oh, actually, over here we need to swap. And then we add R.left. So you're just sort of like telling your explorers, hey, you visit this one, and then you visit this one. And then you visit that one, and you visit that one. Any questions? Yeah.
Isn't one stack enough?
One stack? Why?
Because if you just put both of them in at once,
Mhm.
and then you pop them out at the same time.
So that's a good point, but you pop them out at the same time, but when you're processing them, you're adding like separate children, right? So then if you pop the next two out, so first you'll pop these two out, right? But then you'll just pop these two out, and those aren't the ones you want to swap. Because we add like the children, right? So if you pop two out, you're not guaranteed that the order is correct.
But if you add them in the correct order, like if you add in the left child of the left side and the right child of the right side, and then the left child of the right side and the right child of the left side.
But then the stack is going to work in a really awkward way where if you add this, and then 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 you pop this, and then you add this, and then you add this, and then you pop. Actually, good point. Do you think it would work? Who thinks this will work? Let's do the two stacks to keep things simpler, and then I'll think about this like after my midterm, and then I'll get back to you. Okay. But with two stacks, does this make sense? Okay. So then we kind of just like repeat this until we're out of nodes, right? So here, let's initialize our stack. And what is our stack going to contain? Tree nodes. Okay, and then I'm going to copy this, the right equals that. And then I'm going to push like the root.left and root.right, right? Or it's, yeah, root. So then we'll say left dot safe push root dot right, and then we'll do right or okay, root dot left, then right dot safe push root dot right. Good. So this is making our stack, giving it like the first two nodes. So then what should be our termination condition? Like, when will we know that there are no nodes left? Right, like when our stacks are empty, right? So while left, so while not left dot is empty, and not right is empty. Because our trees are symmetric, you only actually need to look at one stack, but I think this makes more sense like logically. Yeah. So like because our left and right side have the same structure, they have the same number of nodes, whenever your left stack is empty, your right stack will also be empty. So now we have to pop off L equals left dot pop, and then R equals right dot pop. And just looking at our pseudocode, we have to swap, right? So we're going to swap the numbers of L and R. Are we good? And then now you have to do this ordering, right? Because we have to left dot add L dot right, or it's push, but, and then left dot add L dot left. But then we have to do the exact opposite for the right stack. So right dot add R dot left, and then right dot add R dot right. Now why do we have to do this? Because when you add to a stack, you're enforcing a certain order, right? And we told ourselves here that when we're exploring, we want them to explore in the opposite directions in terms of order. So are we comfortable with that idea? So the solution was a little rushed, but I think if you take like maybe 10 minutes, kind of mull over it in your head, try to draw out like a tree, and just look at how things are getting popped and pushed, then I think it'll start making more sense. And it's a really good primer for the next couple of lectures, because the next couple of lectures you're going to be all about like traversing and using stacks and queues and priority queues. Are we good? Any questions? Okay. All right. Oh yeah. Okay, have a good spring break, and I'll see you guys